We'll try to distinguish all these things with a couple examples today. Okay, good. So here's the picture. We'll try to explain this picture later on. Apologies for the small font on here. There's some pictures of some distributions, there's some truth, and we're going to be running through a simulation study to exemplify all of this. If you've been in any of my inference classes before, you've seen this example, so I'll try to cover it up with a few more examples as well. And you'll be working through this example. You don't have to do the visualization of everything in the simulation study with this example, you just need to write down the math for it. So we'll come back around to that. We were looking at our slideshow and we are basically saying we wanted to understand the probability distribution of P, which is the probability of a coin landing 1 or 0. So, or heads or tails, however you want to think about the encoding this one. So we're going to be looking at that example. So I just want to give you just a quick prelude. We're going to have this simulation study. And I'm going to run this thing, and you're going to see a posterior distribution unfold. And what happened at every step was I was flipping the coin once, and I was looking at the posterior distribution evolve. So I'll do that again, and we can kind of watch that posterior distribution just evolve. So I do have a couple things that I'm plotting, that I'm talking about right here. I've got a likelihood function and a posterior distribution, and all I see is one red line in here, and it never changes. And the reason why is because in this example, the prior distribution I chose was 1. So I multiplied by 1, and my posterior distribution is my likelihood function. So we'll go through that. And then we're going to ask these questions. Which prior distribution should we use, and what is the impact of that prior distribution? Once we feel comfortable with all of this, and we understand what likelihood functions are, sampling distributions, posterior distributions, and we can distinguish all of those, we can move into forecasting and stuff like that. We'll get into hypothesis testing, we'll do MCMC. So I think for the next couple days, we're gonna go relatively slow just to make sure we all have the concept. So if there's questions about the terminologies, now's the time to distinguish everything. You can either ask, you can ask your peers, you can work through examples, but we'll be continuing to see these examples. So I've got a binomial distribution. I'm just going to shut this off for a while and we'll come back to the simulation. But I want to write down the math so we understand what those functions are and how they're moving around. So let's look at an example. Let's look at 2 examples. I think that sometimes looking at 2 examples simultaneously helps us to distinguish everything. A lot of people like to start with the normal example. I usually like to start with the binomial example, which I was just showing. I'll show you why. But why not start with both examples? Example 1. So I'll say xi is distributed as a Bernoulli with probability P. So another way to write this down, I haven't written the IID thing here because I just don't want to continue to write it. So if I don't write IID identically distributed and independent, I mean that. So what I mean is this is some distribution right here and it's not going to change. So every time I sample one of these elements right here, I do the same thing over and over and over again. So I'm going to do this n times. So I goes from 1 to n, so this is my sample size. This model right here is just coin flipping. So presumably, if I flip the coin the same way every single time, and the probability of landing heads or tails didn't change, that would represent this model. So if I took all the heads and I encoded them as 1s, the xi's would represent the 1s. And for all the tails that we saw, the xi's would be 0s. So I'm going to write this down just a little bit differently. This is the sampling model. Sometimes people will just refer to this as the model. I'll distinguish that later on. I think anything that you encode, the prior distribution, all of that stuff is part of your model. So saying that, it's just a glossary term. So if somebody says, this is my model, you can say, is that the sampling model, or does that have all your constraints built into it, your prior distribution, something like that. So it's something you can clarify with just a conversation. So sampling model, I could just write down xi is equal to either a 1 or a 0, and this happens with probability p. And this is going to happen with probability 1 minus p. Now I should be really polite and tell you that p is an element, so I've got some notation for that. It's one of these two things. It's either a 0 or a 1. Oops, sorry. Not element. It's inside of, I'll say 0, 1. So, something to distinguish there. The x's can be 0 or 1s, the p can live between 0 and 1. So it's a probability. So big probabilities are close to 1, little probabilities are close to 0. So that's one way to write down my model. So it tells us exactly what we're going to do, so we're going to just flip a coin to do that. You could simulate that. So if I gave you something that was close to 0.5, you could pull out an actual coin and start flipping it and generate this sequence of 1s and 0s. Now if I change p, how would you simulate these xi's? What would you do? How would you do it? So if all of a sudden I pick this number right here, so I need to fix this to be something, and I say this is 0.4. How would I generate my sequence of 1s and 0s?
I mean, I would do it in code, but I don't know how that actually.
So what would that mean for you?
That means I call the function that I can set probabilities to, but
Cool.
I don't know what that's actually doing necessarily.
So you might call that a binomial 1 or something like that. If you went to R, this would be the same as a binomial 1. So the binomial distribution is the sums of 1s and 0s in a sequence of Bernoulli distributions. So where the first argument, the 1, is how many times you're going to flip the coin. So there's some sampling code to do it. Let's say I didn't have that sampling code for you. How would you do it? What if I gave you, let's just say, and we can use our imaginations, I gave you a uniform random number generator. So I gave you a generator that could generate numbers between 0 and 1 continuously. I understand it's on a computer, so we'll imagine it's continuous, but we'll deal with the finite precision of a computer. What would you do?
Yeah, I was going to say, if you have access to a uniform, then you can make draws from that threshold.
Threshold with?
Whatever it is.
Right, so what he means to say is you generate a uniform 0, 1. If that uniform 0, 1 was less than 0.4, he would call that a 1. And if it were greater than 0.4, so between 0.4 and 1, he would call that a 0. So that's the inverse CDF sampler. So we'll study things like that and try to understand how sampling works in this class, so that'll be a tidbit for us. If you didn't understand that, let's go with the answer. We just go to the binomial sampling code, and we invoke the sampler. We punch in 0.4, and we tell it how many samples we want. And we're at the mercy of the computer to do all of that. That's okay. That's what most of us will do. So I could rewrite this right here, where I could end up writing down fxi given p, and I like to write down right there that this is going to be the sampling probability model. Very often I use the letter f, but I'm going to change it this time, and I'm going to call it probability. So, and hopefully that didn't spook you too much, that I could just change what this function is. It's a function of xi. This is random. And this number is fixed. So if I'm going to sample from this distribution, I need to know what p is. And it can't change as I'm flipping the coin. Otherwise, the distribution would not be IID. And so I could rewrite this down, that this probability function, I know what the probability is. When the xi is 1, I want this to be p. And when this is a 0, I want this to be 1 minus p. We can write that down pretty easily. So I'm going to write it down like that. Xi, 1 minus p, with 1 minus xi. So very conveniently, these are already encoded as indicator events, indicators. So I'm indicating which event happened. And by raising things to indicators, I can turn them on and off. They're acting like switches in this function. So when this is a 1, that's a 1. This is a 0. This whole thing becomes a 1, and this is p. So similarly, when x is 0, that's a 0. This is a 1. This is a 1 right here, so this is 1 minus p. So now I can write it down mathematically. And so not just use set notation to do that. So once I have a sequence of the xi's, this is the probability of each xi being a 1 or a 0. So p or 1 minus p. And if I do that over and over again and I look at the full sequence of that, I could end up looking at what the probability distribution is of a whole sequence of xi's being 1s and 0s. And I might write that down like this. So the probability that x1, I'm just going to give you an example right here to build up the thought. x1 is equal to 1, and x2 is equal to a 0. So maybe I have two things in my sequence. So I'm going to end up writing down x1 and x2, given p. So that's the joint probability of these two events. Of course, as I sample the first one, I don't have any influence on the second one. And so all I have to do is multiply these two things together. So this is going to be probability of x1 given p times the probability of x2. And that happens because they're independent. I want to point out that this factorization happens right here because we know p. If we didn't know p, we wouldn't be able to factorize those two things apart from each other. So this is just like going to Vegas and watching whoever's running the what's the roulette. And they're spinning the wheel over and over again. Presumably they spin at the same time, same way every single time. And looking at the board of the history of that doesn't help you because you already know how many reds and blacks are on the board. Be careful of the greens because that's where they get you. So you'll want to compute those probabilities up front and ignore everything in the history of everything and use your mathematical sense and not get into everything. So we're going to remake this point a couple times that the data is only independent when I know the sampling model, and then I can factorize everything apart. And we'll make that point through a simulation a little bit later.
I missed what you were doing. You mentioned an indicator. Can you explain how you use that, the p to the xi thing?
So this is if probability of xi is equal to 1. All I'm going to do is just take p to the 1. So I'm just replacing the xi with 1.
Okay.
1 minus p to the 1 minus 1, and this is equal to p, right there. So I was just doing some mental arithmetic. This is equal to p right here, and similarly, probability that xi is equal to a 0. For any one of the xi, this is p to the 0, 1 minus p to the 1 minus 0, and this is 1 minus p. So very nicely, I can write this down mathematically as a function, and I don't have this set notation illustrating what the process is. So when I see things written down like this, I'm thinking about process. But when I see it written down like this, I'm thinking about something that I can encode into my computer, and I can use in a mathematical formula. So two different ways to express the same thing. Then we took it a step further, and we said, let's just look at the probability distribution of x1 being a 1 and x2 being a 0. And we just multiply these two things together. So for instance, if p was 0.5, the probability of this happening, well, let me make it more interesting. Let's say p is equal to 0.4. So this right here, this is a 1. This is really just 0.4. And if this is 0, this is a 0.6. So you can do the math, that's 0.024. So that's the joint probability of those two things. So if I wanted to know what the joint probability was of a sequence of events, all I have to do is multiply these things together. And so if I had a sequence, let's call it X. This is X1, X2, all the way to Xn. Then my probability distribution of cap X, which is my sequence of 1s and 0s, given P, I could write this down as I goes from 1 to n, f xi given P. So I just product these together. So this is just my producting notation. I'm producting together these individual samples, sampling probabilities. Again, I often change my notation there. So hopefully you're flexible enough. And what you really want to look at is the argument of the function. So you know what we're talking about. And you'll know whether or not this is discrete and this is continuous, and you'll understand what the bounds are. So hopefully you're nimble enough so when I make a mistake and I change my letter right in the middle of it, you go, it's still the sampling distribution of xi given p. So, and that's what that is. So, and this is some formula, and I can write it down. So I can rewrite this down right here. I goes from 1 to n. This is going to be p to the xi. 1 minus p to the 1 minus xi. And I know some rules about products and how I bring them into exponents. And so this looks like this. P to the sum of the xi. I goes from 1 to n. 1 minus p. N minus sum of the xi's. So when I have a product out here and I bring it into the exponent, I slide that through with a sum sign. And so when I rolled my sum sign right across this thing, it summed that up n times, and I didn't like writing down sum of 1 n times because that's confusing. So I call that n. This right here is the total number of ones in x. And this right here is the number of zeros in x. So you might call this the number of successes or the number of failures or something like that, and attribute meaning to the ones and zeros. So the ones are always the good guys and the zeros are always the bad guys. So that's what a sampling distribution is. And I can write that thing down. So I've got this mathematical formula for the sampling model. So we built it up by understanding the sampling model for the individual elements. And because everything was IID, making the joint sampling model was as easy as taking a product. So our sampling model for x, which is x1 to xn, looks like this. Because I like to write a lot on the board, eventually I'll start dropping those the scripts on my summation symbol. And so you'll understand what the operators are. When we have a cap sigma representing covariance and I have summation operators, then I'll be more specific. So early on I'll try to be really specific, later on I'll go a little bit fast. So this is my joint sampling model. So I have my sampling model for the individual xi's, and from that I can make my sampling model for my vector of x's, my sequence or my set of x's, whatever words you want to put there. So now I want to distinguish real quickly the likelihood function. Can anybody tell me what it is? Dylan says, so I'm going to guess where you're pointing. Right here. Right there. That one. This one, not that one. Are they equal to each other? Kind of, right? And so what Dylan means to say is they look the same, but they're not the same. They're the things that you cannot tell until I tell you what the meaning of the things are on the board. So real quickly, this is random. These are the things that are happening with probabilities p's and 1 minus p's, the individuals, and this is fixed. So if I'm going to generate the xi's, I need to know p. If you take p away from me, I don't know how to generate it anymore. So Colby gave us an algorithm, we needed a threshold, we need that number to do it. So without knowing p, I can't write down this probability and generate these randomly. So Colby says, or sorry, Dylan says, and Colby would say, it's the same equation. And you would write it down like this. I goes from 1 to n, 1 minus p, n minus sum of the xi's. So it looks like the exact same formula, but we're going to change our notation a little bit to try to give the reader a clue as to what we're trying to express. Chris?
Just on the definition of sampling model, so is it the model that generates your xi's, or is it the probability of those xi's?
If I knew the ones that generated the xi's and I know they're independent, knowing one tells me the other.
Right.
So I would probably say the joint sampling model is the sampling model because you're going to generate n things, but just be careful when somebody asks you. So if you mean the individual things, if things are correlated and things like that, it can be a little bit trickier. So, but I tend to think about the joint sample because that's what I'm going to do inference off of. So when you talk about the sampling model, I'm usually going to be thinking the joint sampling model. You're going to tell me all the mechanisms of generating data.
Okay.
If you're in a measure theory class, they're going to bring you back to the elements because that's the thing that defines the measure. So be careful. So from a practitioner's point of view, joint sampling model, because that's what I'm doing inference off of. If I'm a theoretician, I can learn everything from the individual sampling. So I got a likelihood function, and what I want to express is this is not a function of this stuff anymore. These are no longer random. Those are going to be fixed. So that's going to be after I observe a sample. So the likelihood function you can build after you observe a sample. Let me just write this down, aka after x is observed. So likelihoods are conditioned off of x. What I want to point out to you is I could know this cap x right here. I could know the whole vector, but when I write down this formula, all I really needed to know was what the sums of the xi's were. So I needed to know how many successes there were or how many failures there were. So I don't actually need to know the whole vector to form this equation. All I need to know is these sums. And if you've taken an inference class, you go, oh yeah, that tells me that that is the sufficient statistic, is probably minimal sufficient statistic, and I can prove all that stuff. So I'm going to give you some notation. I'm going to write this down like this. Likelihood of p given x. And I'm going to write it down as, for just the moment, I'm going to say that's equal to this. Just because it's the exact same formula over here. So, and what I'm going to express with this notation is this is the argument. It's what's variable. Keep in mind, I didn't say it's random. That's a technical word. That means that it's a random variable. If I sum over the sampling distribution, it sums to 1. So if I sum everything up in that space, it's bounded by 1. It lives between 0 and 1. So random variables have additional properties than just arguments and functions. And so for a likelihood function, there's no guarantee that this thing integrates to 1 or anything like that. And I've already told you, likelihoods are self-relative. So I can multiply them by any constant and move them up and down, and they're the exact same likelihood functions. But I'm going to say this is the argument, and this is fixed. So the sums of the zeros and ones are fixed. I know how many there were because I've already seen the sample x. And I was able to compute the sum of the xi's out of it. So the x's are fixed, so the sum of the xi's are fixed. So that's also fixed. That's fixed as well. So the argument is key in this function. These functions on the chalkboard look entirely the same, but they're arguments of different things. This function right here is a discrete function. So, and I could look at all the different ways, all the different possibilities for this sum of the xi right here. It could have been 0, it could have been 1, it could have been 2, it could have been 3, it could have been 4. They're counts of successes all the way up to n, and it's bounded by n. So it's a discrete number, it's an integer between 0 and n. P here is a continuous number between 0 and 1. So let's look at those just real quickly. Plots right here. Here's a binomial distribution. So what I ended up writing down is something slightly different. I want to look at this formula. The x's in this formula relate to the sum of the xi's. So it's just a dummy argument. And this is a distribution. So some of you, and hopefully all of you, are familiar with the binomial distribution. Yes. Good call. Some of you will be familiar with the binomial distribution. And a binomial distribution looks just like that sampling distribution of zeros and ones, but a binomial distribution is a little bit different in that they don't care where the zeros and ones occurred. All they care about is the sum being the sum. So if I had 4 out of 10 things being ones, I could put those ones in lots of different positions, and I might not be interested in the actual orders of those zeros and ones. Binomial distribution has the same kernel, but a different normalizing constant, and I'll talk about that in a moment. So if you've taken a Stat 101 class recently, or any probability class, you understand already. It's just the ordering thing. But this is a discrete distribution. My n here is 10, so that's how many times I flip the coin. And I could look over all the different ways that I could come up with 4 successes in 0 failures. Each one of them would have a vector of p times p times p times p, and then it would be 1 minus p raised to the 6th power for the other 6 things that happen. And then I could reorient it where those successes happen in lots of different ways, and I could add those probabilities up, and it's this number, whatever that is. So we could compute it exactly if we wanted to. The likelihood function, regardless of how I think about the data, if I generated n things at once or if I generated it sequentially, the likelihood function is still the same. So in terms of p, it's still this function. Let me show you a picture of that. That is likelihood. So imagine the sum of the xi's was 3, that's what this represents, and was still 10. My likelihood function is a continuous function that lives between 0 and 1. And I've been as rude as everybody else, and I didn't make my notation consistent. Normally I would say this is the likelihood of p given x. As soon as I call it a likelihood, you should get the idea and know what the argument of the function is. So how do you build a likelihood? You write down the sampling model. And then you plug the data into it and you take all the unknown parameters and you turn them into the argument of the function. In this example, there's only one argument. So later we'll look at binary arguments and as high of dimension as you want. So very different things. So sampling, distribution, and the likelihood function, they look the same on the chalkboard, but they're entirely different things. As Dylan says, that means they're the same. So I'm going to see how you use it on your homework, and I'm going to see how you use it when you're doing test problems and things like that. So it's not going to be a huge glossary thing. You got to get it exactly right. So when you write a paper, you'll probably want to distinguish this for people. I have seen over and over again people say, here's my sampling model and my likelihood. Boom, one equation. And that's pretty lazy. I get it. I can move on. I want to get the point of their paper, and I'm not going to harass beyond them when I see them. So keep in mind, they are two entirely different functions. So what does a Bayesian do with all of this? They write down this likelihood, and they multiply it by a prior distribution. So to form the posterior, and that's what it looks like. So let's just write that down, and we'll fill in the steps after we glance at the normal example. So I want to do this all over again. I'll tell you why I like this example more than the other example, and you can decide for yourself. So example 1 is still XI's Bernoulli. Bernoullis are the same as binomials with one success. It's just one flip of that point. So XI's Bernoulli, right here. I've written down the likelihood function for this problem. And instead of writing equal, I'm going to write proportional, and you'll see why in a second. So, and it really is because likelihoods I can multiply by any number, and they raise up and down, and when I compare values to each other on a likelihood curve, I always do it in a ratio sense. So whatever that constant is I'm multiplying by, it doesn't matter because it cancels out the ratio. So the likelihood looks like this. P, sum of the xi's, 1 minus P, n minus sum of the xi's. And I want to point out, this is the way I built up the likelihood function for the Bernoulli model by flipping the coin over and over again. So this was just the product of p's and 1 minus p's. So just note, a binomial distribution is this. N choose sum of the xi's, p to the sum of the xi's, 1 minus p, n minus sum of the xi's. So if you're more familiar with the binomial and you said, I don't like your vectors of zeros and ones, I'm going to sum them up. It's the only thing that influences, and I'm going to transform that distribution into a distribution not of n zeros and ones, but of a one-dimensional thing that lives between 0 and n. So, and you could build up that distribution, and it's the binomial distribution, and it looks like this. And you can write this down as probability of sum of the xi's given p. And I'll be real polite, and I'll put the n in there for you. So you can see that this depends on n. So it's this distribution, and if you sum over all the possibilities for the sum of the xi's, take on a 0, a 1, 2, all the way up to n. If you sum those all up, this function would sum to 1. So if you summed over this argument in all of its possibilities. Keep in mind, this has the same likelihood function. So exactly the same likelihood function because this is a constant. It's just making sure when we sum over the random variable, the xi's, or the sum of the xi's, depending on how we want to think about it, it sums to 1. So that's a constant. It's not a function of p, so this is just a multiplicative constant. So I could multiply this by this number right here. It's just some number. Or I could multiply this by any arbitrary number I want. I'll call it 5. So, or how about 5,000? So I prefer not to write down any of those numbers. 5,025.2 is another arbitrary constant I can multiply by. And I get tired of multiplying by arbitrary constants, even when they look fancy. And so as soon as I have the function, and it's expressed in terms of p, I usually multiply it by 1. So I don't have to write it down. So the binomial and the joint sampling distribution for the Bernoulli process have exactly the same likelihood functions. So it looks like this. So the posterior distribution, oftentimes I use a pi or something like that, and I'll try to distinguish the notation a little bit, but again, I'm super inconsistent about this, and so is everybody else. So try to be consistent in the same problem. I'll probably change this up. So I'll say pi p, that's the parameter of interest that we're trying to learn about. What is the probability of these coins? I want a probability distribution of that to assert some uncertainty over what I believe that probability is. Given my x's, I'll write it down like that. And I'll say this is equal to my likelihood function given x times my prior p. This is the prior. Divided by the integral of the likelihood function given x times pi p. I'm going to integrate this over p. This is a function of the data, and I'm going to integrate this between 0 and 1. It's a definite integral. If you want to write this down just a little bit differently, a lot of people will call this f of x. And this is, depending on how you write it down, it depends on if you've normalized it. You may or may not agree with your frequentist friend, depending on how you've normalized that function. But often people will express that as the margin of the data. So keep in mind, I could have multiplied this by any constant c, and they would cancel each other here. Bayesian is interested in this posterior distribution. So all this is doing is just normalizing this function. So posterior is likelihood times prior, and this is just normalizing it. So when I add up all the possibilities of p in continuous space, i.e. I integrate over it, it integrates to 1. Please.
Sorry, do you typically consider the inside of the integral the f of x, or is that the whole integral?
Say it again.
Is f of x just the piece inside of the integral, or the whole integral?
It's after I've integrated it right here, so it's this thing involved.
It's the whole thing, okay, thank you.
So I'm distinguishing, and one thing that's good to notice right here is this stuff in the integrand is a function of p. Once I've integrated over p, and it's a definite integral, there is no p in this expression. It's gone. We've averaged it away. We've marginalized it out. However you want to think about it, p is no longer a part of this. So this is just a function of x. And I think in terms of just stating it's a function of the data, it's being used to normalize everything. This kind of looks like Bayes' theorem. So Bayes' theorem looks like the thing when I flip that around. But keep in mind, whether or not I put down the joint sampling model or I use the likelihood, as long as I'm moving p around, I'm treating it like the likelihood. So I like Bayes to look like likelihood times prior. And then everything else is just normalization. So, and that's my articulation of Bayes. How do I think about it? I like doing likelihood-based inference. I want to know what p is. The likelihood function about tells me where it is. And the prior distribution gives me properties about my inference. I say it like that because I'm trying to sound objective. So I could also say, well, I don't know, I like curves that look like this. And that's what my probability distribution is on 0 to 1. And I probably wouldn't convince you. So I need to give you reasons for picking this prior distribution, and we're going to look at reasons. And I'm going to give you some good ones, and a lot of the class is about coming up with more good reasons. So for this thing, I can think of like 7 good reasons to pick the same distribution, and I need a little bit of time to tell you about all of those reasons. So that's how we're going to conclude. And that red curve that I was drawing, it where this was 1. I just placed a flat prior between 0 and 1. I respected the bounds, so I just used a uniform distribution. I didn't upweight or downweight anything between 0 and 1. And so my posterior distribution was just a normalization of the likelihood function. And that may or may not be a good idea. So, and that's what we're going to study. But that's Bayes. Let's just look at a normal distribution real quick. I'll come back to the prior. I will ask you guys what you think a good prior is going to be, and you're going to say a uniform distribution. And then somebody else is going to say a beta. And then we're going to discuss all of these possibilities. switch the example real quick and make sure we've got the right idea. So, example 2. I'm going to say xi's are distributed normally with mean, mu, and variance sigma squared. So I can draw you a picture of this. Looks like this. Centered at mu, and this is my sigma right here. I apologize, it didn't line up exactly right, but you can use your imagination. So if you don't know, sigma is the distance from this to the inflection point there, so I drew that wrong too. So that's actually where it inflects. So, but my imagination works well enough. This is a normal distribution. And so I'm going to grab xi's continuously. This thing goes way down there, way over there, off to negative infinity, which means any small number you can think of, pick the absolute value of that thing, raise it to that number, do it again, do it again, do it again, throw the sign back on it, and it's bigger than that. So, in magnitude. Same thing in this direction. So this lives between negative infinity and infinity. And it's concentrated around mu. And sigma helps us to understand how strong that concentration is. This number right here lives between negative infinity and infinity as well. And this number is always positive. Remember, it's measuring this distance in here. And so this is a number that lives between 0 and infinity. And if you say the normal distribution has 0 variance, I'm okay with that. That doesn't really deeply bother me. That could bother somebody else, but I'm just going to imagine that's a point mass distribution. And I would have described it differently. So I'm going to remove 0 is the possibility in there. And I'll agree with Wikipedia. So they'll also say that that has to be positive. So that's what those things are right here. So we might have a couple different Bayesian goals. So I could try to learn. So this might be goal 1. I'm going to call it goal 0. Because I'm going to replace this in a second. I could try to learn both of these parameters, mu and sigma squared. Given x, all of my data, so I'm going to sample n times. I'll often forget to write that down, and you're going to probably ask me about it. Are we doing this n times? And I'll say yes. And then when we get to the binomial model, I'll say you can if you want, but I've already used n. So sometimes my answer will change. So maybe I want to learn that right here. I want to do this n times, so this is just a vector of x1 to xn. Or I could have a different goal. Since this is a classroom, maybe I don't want to learn everything all at once, and I want to do it in steps and understand what the breakdown of these steps are. So maybe I want to learn this, just mu, and I'm going to assume that I know sigma squared. Bless you. So this is a different posterior distribution. This is the joint posterior distribution. So this is a 2-dimensional distribution in continuous space where this thing lives between negative infinity and infinity, and this lives in the positive plane. So this is a distribution just on mu where sigma squared is fixed. So this is treating it like I know what sigma squared is. You've given me the variance, and now I'm going to use the x's and the variance to learn what mu is. This is a 1-dimensional distribution. And similarly, I could learn this one. And that's a little bit of the navigation of how I'm going to route through this class. I don't want to do the harder one first, but this is obviously what we want to do. So the books usually have you do this one, and they don't move on to that one for a while. So I think what we're going to do is we're going to make this goal 3. We're going to learn this one, and we're going to learn that one. And when we learn this posterior distribution and this posterior distribution, you'll say, there isn't an instance outside of a classroom where I ever use this distribution, because nobody ever gives me the variances. And you would say, this is even more ridiculous. Nobody ever gives me the mean and asks me to learn the variance. There are examples like that. So I would agree, nobody ever gives me the variance, but there are cases where I lost the mean, and into place and I learn the variance. So in a spatial analysis, a Gaussian process, usually you center all your data, you force it to 0, and what you're trying to understand is spatial variability. So that's just a side point. I'll point out, once we learn these distributions, we can use these computationally to learn this one. So being able to understand this and visualize it can be a little bit difficult because our minds don't work well in higher dimensional spaces. So we're going to learn this one, then that one, and then I promise you we'll use these two things to build this up. And so if you don't know what a Gibbs sampler is, I'm going to explain what a Gibbs sampler is using these two distributions. So it doesn't really matter when I build up these three distributions, because at the end of the day, I still need to write down the likelihood function. And it really just is concerning which priors do I use for all of this. So for this one, I'm going to need a prior on that space. For this distribution, I just need a prior on mu. And for this distribution, I just need a prior on sigma squared. So the notation helps us to understand where we place the prior. Most people will not be so polite and tell you what's fixed in here. So you need to look at what they're wiggling around to know. Sometimes people write this down and they'll call it this distribution. To me, this means a little bit different. It means you integrated out sigma squared. But if sigma squared was in the equation off to the right, I would know, oh, you're treating it as fixed. So keep in mind in the literature, everybody's come up with every variation, and my notation is designed to try to sort this out. I don't even follow it fully when I write papers. Okay, so let's just write down the likelihood function. For example, 2, and we'll leave it there, and we'll come back and we'll address the prior distribution for the binomial example. We'll understand what the answer looks like, and then we'll understand how to mathematically derive some of the properties that we see in the simulation study. So just real quickly, for this example, what is the likelihood function? And I could write it down like this. I could say mu sigma squared given x, where this is just a vector of these draws. There's n of them, they're discrete, and they came from a continuum. So they live in a continuous space. We have a discrete representation of that space. We're going to try to learn from it. So I'm going to write down my proportional sign, meaning I can multiply by any constant, and it's still the same likelihood function. And I've got some distribution right there. F of x given mu and sigma squared. And for a normal, I know what that looks like. That's this curve. So that's what that looks like. So let me rewrite this real clearly. 1 over square root 2 pi sigma. If you like your sigmas to be squared at all times, suck it inside right there. So I oftentimes pull it out and sometimes I move it back in depending on what I'm doing with the parameter. E to the minus 1/2 xi minus mu squared over sigma squared. That's a normal distribution. So as the xi's get farther away from mu, this number keeps growing bigger and bigger and bigger. Once I put a negative sign in there, it's getting smaller and smaller and smaller. So more and more negative, which is slamming this thing down. That's what's happening in the case here. So it's slamming them down, and it's doing it at this quadratic exponential rate. And you're stuck with that in a normal distribution. When we talk about t distributions, we have more control over that rate. So it comes down a little bit slower. But this is what that function looks like. And I can just bury this thing right in there, shove it in here, and product it up over and over and over again. So, and I will have the likelihood function for mu and sigma. Now I want to point out a couple things about this. I've written down too much. This part right here, if I just keep producting this into each other on a computer, eventually you will turn something that's not 0 into a 0. And so multiplying small numbers into each other over and over and over again gets really small. And eventually this will wipe everything out into a 0. So I will say there's also all kinds of computational problems here, but we'll just focus on the easy one first. What I could do is just get rid of it. Get rid of it. It's the likelihood function. This is not a sampling distribution anymore. I'm looking at the function with these arguments in it. And I'm moving these things around. I've got sigma squared over here, got sigma squared here, and I've got sigma here. So it might be nice to make that sigma squared and then put the half power right there, so that I can think about this exactly the same as that. That's what the likelihood looks like. I want to point out, if I were doing this inference, this is exactly what I would do. I would just copy this thing together and I would have a formula. And I could do the exact same thing for either one of these. And there would be no problem with doing it. But I could take some shortcuts and save myself some time. So if I weren't doing inference on sigma squared, i.e. it was known, I could also get rid of that. But if I did that, and I try to do this problem, sigma squared is not a constant, and it won't cancel out of everything, and I would have just made a huge mistake. So there's different ways you can express this likelihood function, and different ways you'll do it on a computer because it'll simplify the calculations, but in spirit, take the joint sampling distribution and product it up if it's IID, and you'll always get the likelihood. Then look at all of the stuff out in front of the distribution and see what you can cancel out. So for the joint, do not get rid of that. For inference on sigma squared, do not get rid of that.
But for both one, we can.
For this one, you can. And you can toss this. And I'll give you a hint. What happens right here is the likelihood for this problem, and this is very special, we'll go through this calculation next time, is I can write down the likelihood function really easily. It looks like this, x bar, where that's just the arithmetic average, minus mu squared, sigma squared over n. And I can do this without a product. Keep in mind there's a sum sign up here. So that won't be obvious that I can just say this is proportional to that thing until you work through the algebra. So I think we'll kick it off there next time and come back to the binomial example. And pretty much after we get through this series of exercises, you'll have it after homework 1. So homework 1 that will be out on Friday, it is already posted. First exercise is write down the likelihood function for the normal distribution and the answer is this. Or it could have been this, depending on the way I ask the question. So we already have some homework. That's it for now, you guys. No review tomorrow, but we will do a review next week and the week. See you on Friday.
I think that is due the 6th, 0.
Okay, so that's due Friday, not last one.
This Friday.
No.
Yes. Yeah, I think that's right. And that's just, you just have to compute the posterior expectedness. So, yeah.
I was like,
The stats is this where
Oh, I see.
basic rule of
Yeah, I also wasn't here on Friday, so
So it gives you a combination